Is the writing pad visible?
Yes, ma'am, visible.
I think we should wait
Yes,
for 5 more minutes. Let's see whether someone else joins or not. I don't think it was visible earlier. Now I'm sharing again. Just 1 sec. Yeah, it's visible. Okay, let us wait for 2 more minutes. Then we'll start with
okay,
today's
okay,
session. Yeah, okay.
okay, ma'am.
Okay, should we start?
Yes, ma'am.
Okay. First of all, have you attended the classes or should I go to the briefing? Okay, let's see. So last last week 2 sessions, what sir have taught, let us go through that first. So first of all, one very important topic that sir taught is like there were some different contents, like what should I say, like density, viscosity, those terms were being introduced. So let us go through the briefing of those terms first, so that if you have not even taken the classes, we can get a recap of all those. So what is density? Let us consider a fluid element like this. If this is a fluid element and its mass is delta m and its volume is delta v, then density is what? Delta m upon delta v, right? And we
Yes,
tend to write limit delta v tends to 0. Why? We always, when we are terming like this, we tend to write like this so that we can convert it to differential. But when velocity is too small, like if it tends to 0, then what happens is that the system becomes like there are very small number of particles on a very small amount, small volume. So what happens there, if we plot density versus length scale, like if this is the length scale of that of this fluid element, then what happens, there are random fluctuation. if delta V is very small. After this random fluctuation, it becomes static like this, and then it starts increasing. So this is the region that we need to focus to, this region, right? Because after, if we will increase this too much, then we tend to find that gross density, right, by continuum hypothesis. If it is very large, then and the large number of molecules are there in the volume that we are considering, then it is very difficult to take a gross amount. That's why we tend to keep the volume in between this V, and in between this, let's suppose if it's V1 and V2, we tend to keep the volume in between that. Oh, sir taught in the class, no, like we will represent volume like this. Why? Because velocity also we are representing by V. So if so that we don't get confused in between both of them, we are using this symbol for volume. Okay. So now, so the velocity should not be zero, rather it should be some small volume that will scale with what? That will scale with length scale to the power cube. Have you understood this? And this length scale will be equal to lambda cube. What is lambda? I have taught in the previous class, previous session. That
Mean,
is lambda, yeah,
mean free path.
mean free path, correct. So as volume is like like L cube, that is its dimension is cube, so we will consider this in cube. So this will scale to lambda cube. And if the volume, that is minimum volume, that is greater than this lambda cube, then we can say that the density is constant, right? So this was one thing that that was introduced. Another thing that was introduced in the class was, just one second, that was bulk modulus. Can you say what bulk modulus is? Okay, let's see. Bulk modulus is like, if there is a body, we are applying some pressure over there, there will be change in volume, right? So if there is change in volume with the change in pressure with respect to some specific volume, that is called, that is given by the quantity bulk modulus. That is bulk modulus we can write as delta P delta V by V. Why minus? Cos if we will increase the pressure, let's suppose on a small body from all direction, what will happen? Its volume will decrease. Its volume will decrease. That's why we are giving this minus term. That is it. They are inversely related to each other. Now, if we want to represent this V in terms of density, what we will do? We know that mass is equal to density into volume, right? Density multiplied by volume. So if we will take ln on both sides, ln rho plus ln V, and if we
Yes.
will if we will differentiate all of them, what will happen? Mass is consistent for a small body, right? So if mass is constant, this will become 0, and this will become 1 upon rho d rho plus 1 upon v dv, right? So we can see
Yes.
dv upon v, what will happen? This is minus d rho upon rho. See, so if we will put in this bulk modulus formula, then it will be dp d rho by rho. What does this means? This means that like if a body is there and we apply over there, then density increases. Like in thermodynamics, if you had studied through that, we know that if this is a piston and there are a lot of gas molecules over there, if we are applying pressure on this piston, what will happen? This will move here, and the per unit volume, the number of particles will increase because volume is decreasing, right? That means
Yes.
if we increase pressure, density will also increase, as this is given by this formula as well. This formula also shows that it is directly proportional, right? Now,
Yes.
we also want to rate this with what? With velocity. So how we will relate this to velocity? Let's suppose, let me change the color. Yeah. Let's suppose a kinetic velocity is applied on a body, because of which the pressure on the surface increases. So pressure increases, so pressure scales to what? Half rho, because both are different forms of energy, right? So pressure is given by because of the kinetic energy that we have applied. So pressure, if we write from this formula, we can see that pressure del P is equal to K del rho by rho, right? From here, we can get this K del rho by rho. So if it is K del rho by rho, that will scale to means these orders are same, right? These are not equal. Orders are same. Scale to means orders same. The order of both of them, because both are different forms of energy, we can write their orders to be same. So this is half rho u square by k. No. So rho, not rho. Yeah. So just one second. I have written, yeah. So if we write, yeah, del rho by rho will be half u square rho by k. So if we will write this, what will happen is that k by rho. Just one second. Let me delete this. Yeah. So what will happen? This k by rho thing. This k by rho, this thing, we can write as sonic speed. So root over k by rho is equal to sonic speed, that is a. And what is this a? What is this a? This a is the velocity by which the disturbance, like let's suppose there is a wall and wall is static and a fluid moves through the wall. So what is happening? There is a disturbance being introduced by that static wall to the fluid. How? That static wall is like this wall is stationary, and the fluid layer that will come in contact with this wall will be stationary, will become stationary as well, because sir taught in the class, like there will be exchange in momentum in between both of the layer of fluid in contact with the solid wall, so it will exchange momentum. And as the fluid will bombard, that is there will be Brownian motion, right? So there as it will collision will take place between the fluid particle and the wall, there will be there will be collision. Because of this collision, there will be exchange of momentum. I am talking in terms of gas. So there, that exchange in momentum, what will happen? Because of that exchange in momentum, the fluid in contact with the wall will become rest in like it will lose its velocity, and because of which the if this is the this is the solid boundary and this is the fluid, then let's suppose this in contact with this will also become rest. And this is what we term as disturbance. This disturbance will be transferred to the whole fluid like this. I'll tell you in the later parts, like how it is done and which term will indicate the disturbance transfer. I'll tell you all those. But for now, this disturbance is transferred onto the whole fluid. So this disturbance, the velocity of the transfer of this disturbance is given by the sonic speed A. Okay, so if we will replace this over here, then what will happen? Del rho by rho will scale to 1 by 2 u square by a square, right? So del rho by rho. Now this u by a, we can represent it as Mach number. What is Mach number now? I think you have heard, like if we give an example, like a hose is there and water is coming out from there. So this hose is having like Mach number 10, let's suppose. So Mach number means the velocity of the fluid, like velocity of the fluid in that medium with respect to the disturbance. A means disturbance, the velocity of the disturbance. So with respect to the disturbance, what is the velocity of the flow? fluid. So that is given by Mach number. So we can write this, Mach number is U by A. So we can write this as half, sorry, not equal, that will scale to half of Mach number square. So this Mach number is directly like linking to this density, right? That means like change in density with respect to the original density. That means it is being an indicator of the compressibility of the medium, right? Of the fluid, not medium, fluid.
Yes.
So it like if Mach number is high, the density change will also be high. That means the fluid is more compressible. So let's suppose so I have given you a broad idea of this Mach number. Let me show you, like if let's suppose the density change is 5%, then we can write this as uh, if the change in, see, no fluid is like, we can't say that in practical terms fluid incompressible, like it can't happen at all. Like there will be compressibility, right? That means if we will apply
Yes.
pressure to a fluid, its density is bound to change, right? But if that change is very small, negligible, then we are terming this as fluid is incompressible. Like let's suppose the change in the fluid velocity, sorry, density is less than 5%. That means change in density with respect to pressure is less than 5%. So if we will write this in this equation, this 5 by 100 scales to half of Mach square. So if we will solve this, we find that Mach number will scale up to zero point 0.3. That means if Mach number is less than zero point 0.3, the effect of compressibility is not that much, right? That means if Mach number is greater than zero point 0.3, then only like effect of compressibility we will take into place, right? Have you understood, or you are having some doubt?
Yes, ma'am, understood. And for this, we call it the sonic, no? Point
Uh,
three less
what? Pardon? Can you tell again?
or the Mach number is less than point 0.3 means which flow this one? Sonic.
Not sonic, nothing. You forget all those sonic and everything. Mach number less than zero point 0.3 means what? Means this delta Mach number is directly proportional to, like not proportional to, but it scales to change in density, right? That means if Mach number is
Yes.
very small, that means change in density itself is very small. What does that mean? Means if I'll be applying pressure to the body, the change in density will be very less. That means we can consider that body to be in like that fluid to be incompressible, though it is not, but
Yes,
its change is so small that we can neglect the compressibility factor, right? Have you
yes,
understood?
ma'am, understood.
Okay.
Yes.
So there are some very other terms like that was being introduced. If we will go through a bit of those, then it will be helpful for us to solve the problems that will be upcoming, right? So another thing that sir has taught is viscosity, and before viscosity we will understand about low no slip condition. I've already told you now, what is no slip condition. Like if a wall
Yes,
is at
ma'am.
rest, there will be exchange in momentum between the fluid and that solid wall. That's why what will happen that that fluid that is in contact with that wall will also come to rest. That is no slip condition. So what will happen? Let's suppose there is a solid wall, right? And there is a particle that is present in that wall, and this is the free stream velocity. Like this is a solid plate and this is a fluid particle. Let's suppose we are considering a fluid particle, and this is u infinity, that is the free stream velocity, that is a fluid coming here that is moving on the top of this plate. And now, we are considering only one particle, that is like we are taking that into consideration, that particle, right? So now there is like because of the no slip condition, there is zero tangential velocity of the fluid particle. But why? Fluid molecule 1 comes in contact with the surface and exchanges momentum, that I have already told you. And as it comes, like if there are lots of fluid particles and it comes and it comes in contact with the surface and that bounces back, because of this it will exchange the momentum with the surface, and because of this exchange momentum, this fluid part, the fluid layer just in contact with that plate will be at rest, will become at rest if this wall is at rest. This is no slip condition. Now when the no slip condition is not valid, we also have to take those conditions into consideration, right? So gas molecules, let's suppose the system is very rarefied. That means if fluid is passing from here, that means if fluid is passing from this side and like the particles that are present in the fluid are very small, that means the particles that will come and collide with the solid surface is very small. Numbers are very small, right? So what will happen, the exchanges momentum that will be happening between fluid particle and the solid wall won't be sufficient. So if the momentum exchange won't be sufficient, the what will happen, the fluid particles that in contact with the solid surface won't come at rest. So no slip condition won't be valid in that case. Another thing, when another two conditions is that when no slip condition, boundary condition won't be valid is, have you heard about phoretic motion? Let me tell you, is there, if there is local strong like strong temperature gradient, like let's suppose if this is the plates, the solid plate, right? And at this point I have applied one burner and I am heating this point. So what is happening, there will be a local temperature gradient on this. If and we know if this is gas particles, I have already told you we are considering this as gas particles. If gas particles are there, so what will happen, this point, at this point the particles will be having more random motions. So because of what, there will be one induced motion in particles in that region itself. So there will be slip on that surface cause because of the self induced motion. So that is called phoretic motion. And if it is introduced because of the temperature gradient, local temperature gradient that I have told you, this will be called as thermophoresis. Thermophoresis. Okay. Now this I have already told you in case of what will happen if that fluid is gas. Now what will happen if that fluid is liquid? Let's see. If the fluid is liquid, see, the solid that we are seeing here, that is not in microscopic point of view, that is macroscopic point of view. If you will place a surface under a confocal microscope, that will give you a 3D structure, like 3D visualization, or you can do AFM as well. So that will show that a surface, any surface will have these bumps in the microscopic level. So what will happen if fluid particles is like the fluid particles are liquid, then what will happen, they'll get trapped inside these bumps. And there will be van der Waals force between the solid and the fluid particles. But the hydrogen bonding, like if the fluid particle is water, the hydrogen bonding in the water molecules are so strong, that means like if one particle will be trapped here, it will pull the other particle also here. So more than van der Waals force, this hydrogen bonding will trap all the particles here. So if this wall is static, the fluid particles will also become static. So this is one condition. Another condition is, have you heard about carbon nanotubes? Anyone?
No,
What did you heard about that?
I didn't.
Huh?
For communication purposes, is that?
No, carbon nanotubes. That is actually, see, there are lots and lots of structures of carbon, like carbon, they will come together and form different structures, like if you know about uh, let me say graphite, diamond, all are those carbon structures, right? They'll be bonding like strongly with each other and will form a whole structure. So carbon nanotube,
Hydrocarbon,
pardon?
hydrocarbon, are you
Yeah, yeah, hydrocarbon
hydrocarbon?
is also, yes, hydrocarbon is also, that is a product of carbon, right? Carbon and hydrogen. So carbon nanotubes are also one structure of carbon. So what will happen in carbon nanotubes, if you have liquid in contact with carbon nanotubes, there will also be the water, as I already told you, the hydrogen bonding between the water molecules and the carbon nanotubes will be, there will be hydrogen bonding between the carbon nanotube and water as well. But there is more than van der Waals force, there is hydrogen bonding, like what I have already told you. This is an example of that. This type of flow is called highly slipping surfaces, this carbon nanotube. So the slip will be so high that we cannot say that no slip condition is valid. Okay. Now giving this into consideration, we will now study about what is viscosity. Okay. So I already told you about the disturbance that has been introduced by the static surface, right? So the messenger that will take the disturbance from this surface to the whole of the fluid is known as viscosity. In simple terms, the physical significance, right? So let's suppose this is the bulk fluid motion, and let's suppose this is a fluid particle that because of the no slip boundary condition, this came at rest, right? And as it will move away, like the as we will move away from the wall, there will be some velocity, like the velocity will keep on increasing, and it will increase in such a way that after some time it will be equal to the free stream velocity. That means this one, 0.99% of u infinity. That's 99% of u infinity. So this is the velocity profile that will be developed here. But as we will move further to the right direction, what will happen? This velocity, like the disturbance, like you tell me, what do you think? If I will move more towards the right side, what will happen? The length will increase, the length of this velocity profile will increase or decrease? What do you think?
I didn't understand, ma'am, what you asked question.
Ma'am, could you please repeat the question once?
Okay, so see, at there are, let's suppose, point 1 and point 2, right? So in point 1, I have already formed the velocity profile for you, right?
Yes.
So as we will move to point 2, the fluid particles will also travel, like the fluid particles that was at point 1 will also travel to point 2. And that will, after going to point 2, that will face a uh, viscous force on that surface at the point of contact, right, with the solid. So what do you think that velocity profile that will be developed at point 2, its length, that is length of the velocity profile, this is the length, right? This is the length of the velocity profile. The length where the velocity will vary, that is the length up to which the disturbance will be taken from the solid wall to the bulk fluid, right? And it will take some time, like the disturbance will be taken up to some point, like up to this point, this, like let me give it another color. The disturbance will be taken up to this point, right? Up to this point,
Yes.
where the fluid particles will achieve 99% of the free stream velocity. So my question is, like, if I'll move further to the right side, will this length decrease or increase? What does the common sense tell? What do you think?
Yes, ma'am.
They increase.
Yeah, it will increase. Why? Because the friction provided by this surface will be more, right? So as the friction provided more, what will happen is that the momentum disturbance will be propagated more, like it will take more time to reach the 99% of the free stream velocity. That means it will be like this. So the profile generated will be this. This is called boundary layer. I think you have heard about this. This layer is called boundary layer,
Yeah.
right? Now tell me another thing. If the viscosity will increase, let's suppose this is a fluid, right? And the solid surface is same. So if the viscosity will increase, will the boundary layer thickness of this boundary layer, red, the one I have represented by red, this thickness will decrease or increase?
Increase.
Increase. How?
Because if viscosity is increasing, then
I
the
can't.
disturbance will get Hello?
Yes,
Hello,
yes, yes.
ma'am?
Tell me. I can hear you.
Because if viscosity is increased,
Hmm.
yes, ma'am. Ma'am?
I am able to hear you. Tell me.
Visco-
If viscosity
if
increases.
viscosity is
Hmm.
increasing,
Hmm.
then the disturbance will get propagated to more length.
Larger distance. Yes, correct. That means you have
Yes.
understood. So if viscosity will increase, the thickness of the boundary layer will increase as well. So I think you got a brief idea of the viscosity. And another thing that I want to introduce you here, like to you, is that the shear stress. I think if you have you done the classes? Have you taken the classes?
Yes, ma'am.
Yes.
Okay, then you already know that the shear stress that sir have already told you, right? The shear stress is a function of the momentum, velocity, like the rate of deformation. Like let's suppose there is a fluid particle here. Let me use some other color. I'll just give you one brief, then we'll proceed with further questions. See, if this is a fluid particle, I have represented the fluid particle as blue. Okay, so I'm magnifying this here. If this is a fluid particle, so what will happen, this point, like as the fluid particle will move from like one point to another, what will happen, this point A will get displaced to A dash, right? And point D, like point D is upper to point A, right? So as we can see the velocity profile, the thickness will be increasing as will move away from the like from the plate, right? So this D will also move larger distance as compared to A. So if we will take that the velocity profile is like is linear, then it will be like this, like uh, it will move to a velocity u delta t, and this will move to a velocity u plus del u, because as we will move upper layer, the velocity will be increasing. So we are taking it that it is increasing by del u. Can you tell me why? Like if this is layer 1 and this is layer 2, so what will happen in between those layers? Anyone?
Tangential stresses are produced. Yeah.
That is fine, but sir told you in the class, no, that this layer 2 will try to decelerate the motion. That means because this layer 2 is more closer to the solid surface, right? So it will try to uh, decelerate. That means it will try to stop the layer 1, layer 2 from moving front, right? And this layer 2 will try to accelerate the layer 1. So there will be a competition in between those two. That means layer 2 will have higher velocity as compared to layer 1, right? Because the momentum is getting transferred from lower to upper layer. So what will happen, this the d dash will have higher velocity, and if we measure the distance means velocity into time. So u plus del u into del t, and this is u del t, right? And we are taking this thickness to be delta y and this angle to be delta theta. This is u plus del u. So if I'll take tan del theta, this will be u plus del u delta t minus u delta t by del y. What is tan theta? Tan theta is p by b, that is perpendicular. Just 1 second. I am audible, right?
Yes, ma'am.
Yes, ma'am.
Okay then. So p by b, right? So this is p. Uh, this is p. So this is p cos perpendicular this direction, this distance. This distance is what? This u plus del u minus sorry delta t minus u delta t, and upon base. So we are taking this as base, del y as base, right? So if we will negate this, what will happen? This is del u del t upon del y. So this will like approximately be is equal to del theta, because theta is very small. So del theta is equal to del u del t by del y. So del theta del t is equal to del u by del y. So if we will take limit del t tends to 0. So limit del 2 tends to 0. So we will take limit del y tends to 0 here, right? So this will become what? This will be differential. So simple formula of differential. If you will take limit, it will become the differential du dy, right? And this we can write as the rate of angular deformation. That means theta dot. Okay. So we know, we have already known like this du dy. So we need the rate at which the fluid is shearing. Thus there means some relationship between shear stress and this rate of deformation must be there, right? So that is written as shear stress is equal to, that will be a function of linear deformation. So that means shear stress is proportional to linear deformation. The like this is already known. Like if there will be some angular deformation, like there angular deformation as we can see in this fluid element, it will be experienced because of the shear stress that is being experienced by the solid wall. Like the solid wall, at solid wall there will be some shear stress, and it will be that disturbance will be propagated through the whole fluid, right? So this can be equalized by giving mu theta dot. That means mu on angular viscosity. This only this is given by du dt. So this becomes what? Du dy. So du dy, right? Tau is equal to mu du dy. This is called Newton's law of viscosity, right? So we term that also. Now another two terms that was being introduced was dynamic viscosity and kinematic viscosity. Dynamic viscosity is simple shear stress, like we can write from here, it is shear stress per unit linear deformation. So we can get the get the dimension also for this. Shear stress means what? Force per unit area. So dimension of that we need upon linear deformation. Linear deformation means time inverse, right? Linear deformation means time inverse, and this is ml t to the power minus 2 force, and l to the power minus 2 is area, right? And this will what? This will become what? M l to the power minus 1 t to the power minus 1. Now for kinematic viscosity, it is mu per unit density. So kinematic viscosity is C. This gives a feel of what is happening in between the fluid layer, right? See, what does this mu do? Mu tries to diffuse the momentum, like the wall introduced the wall, this is the wall, and this have introduced some momentum, that is it will try to hold on to the fluid, right? So that momentum is been introduced by the wall, and the momentum that is introduced by the wall, the mu will take that momentum to the top fluid, right? It will keep on diffusing that momentum. And what is this rho? Rho will try to hold on to that momentum, because rho is a system property and it will try not to change, right? So there is a competition between mu and rho, and that is given by the kinematic viscosity, or so it is a related tendency of the fluid to create disturbance in momentum as compared to the ability to maintain its momentum. So this only I have told you.
Ma'am,
Yes.
so in this case, like if we have two fluids, one with less kinematic viscosity and another one with more kinematic viscosity,
Hmm.
the one which has less will have less boundary layer, is it, ma'am?
Kinematic viscosity, yes. If it
Okay.
will be more, see, kinematic viscosity is mu upon rho, right? So it is directly proportional to mu. So if the viscosity of the fluid is more, the messenger, like, see, if you can like you can take it as a messenger, so its strength is more. So if strength is more, so it will diffuse the information or the momentum to a larger distance, so the boundary layer thickness will
Okay, ma'am. Ma'am, one more doubt, ma'am.
be.
Like if since viscosity is like a messenger,
Hmm.
if there are if we introduce the fluid between two surfaces, one which is fixed and one which is moving,
Cauty flow, Kuwait flow, whatever you pronounce. Yeah, tell me.
so in that case, like will it propagate that this surface is moving, or it
The
is at rest?
there will be a competition. See, if this surface is moving, let's suppose with some velocity v, and this surface is zero. So what will happen? The particle that is closer to this surface will try to uh, this will try to like keep the fluid particles at rest, and this will try to take it with velocity v. So what will happen? This will this will, it will increase, and it will be forming like this, right?
Okay, ma'am.
So
Okay.
the velocity boundary, like velocity profile, will be like this. So this is a, there is a specific type, this type of flow is called Kuwait flow. Sir will teach you in the class, I think in the next session. So this type of flow is called Kuwait flow. That is one of the plate is stationary, another plate is moving with velocity v.
Okay, thank you.
Yes. Okay. So I think, sir, I won't go too much detail. There are many things sir have explained. So I'll give you for ideal fluid. So ideal gas rather. So we sir have derived in class na rho alpha VTH root over 8 RT by pi. Not VTH. This will be lambda. Just one second. This will be lambda. Sir have taught you this in class, right? Hello. Have you attended the class? This is for
Yes,
ideal
ma'am.
gas. Yes, yes. So this is for ideal gas. Uh, just one sec. So this velocity is actually v thermal velocity because of the temperature that was been introduced. So this is root RT. This is actually a standard kinetic gas theory. So this came from that. So I won't go into much detail. I think sir have covered this already. So we'll just go to another another dimensionless number, that is Reynolds number. So Reynolds number is equal to inertia inertia force by viscous force. Inertia force means what? A flow is happening, a solid wall is there, like plate is there, and the flow is happening. So the as I already told you, the upper layer will try to accelerate the lower layer, right? And the lower layer will try to decelerate the upper layer because of the static wall, because of that momentum. So this is given by the viscous force, the opposite to the flow. And the inertia force is the the upper layer will try to, because of the inertia, you know na, like if there is a Newton's like, see, a bus is there and we are moving in a bus. So when the bus will immediately stop, what will happen? We'll get a forward push because of what? Our body, what, anything? Hello?
Nothing.
Yeah, so what is happening? Our body will try to move in the forward direction, but because of the bus stopped immediately, our lower portion, like the leg will like it will come to stop at like immediately along with the bus, because it is in contact with the bus. But the upper body was at inertia, so it will try to move forward. So that is only happening, that the competition between the inertia and the viscous force. So we can give it as mass into acceleration upon shear stress, because viscous force is given by the shear stress, but shear stress is pressure, so this into area will be there. So this is mass into acceleration. So this is shear stress. Shear stress means what? Tau we have already told in as Newton's law, that is V by L, mu V by L, right? So we are considering it linear profile. So if linear profile, we can write it as V by L. Area means L square. So acceleration means what? Acceleration means V square by L, right? Meter square per second. Uh, sorry. Oh, V square by L, V square by L, correct. So this mass is equal to what? Density into volume. Density into volume, and volume is given as L square, right? So this will be given as, if you will this is rho. L square will be L square, here L, so square will be going this, here it will be L square, and here L, so this will also go, so it will come as density will be there, and this velocity, one velocity and another velocity is there, so V, and upon mu, and there will be what? There will be a density into volume into L. L from here, one L is left. So this L is what? This is the characteristic length scale. Like if a pipe is there and the flow is happening inside the pipe, the characteristic length scale is what? This, the radius of the pipe. That is the characteristic length scale. Okay. Now let us move to non-Newton fluid. I don't think I'll go too much detail in that. So let us go to today's problem solving session. So first question, let me go to the first question. Is the question visible? Just one second.
Yes.
Yes. So what is happening in this like, sir, I have shown some video in the class, right? Like viscometer is there. What is happening in that viscometer? The outer shell, that is the outer cylinder, is stationary, and the inner cylinder is moving at a speed of 300 rpm, right? So we can see, like the question that you immediately, like you told me one question, like right, you asked me one question. Priyanka, yes, Priyanka asked me one question, that if one surface is stationary and another surface is moving with a velocity v, then what will be the velocity profile? Like, see, here also the velocity profile is same. So actually it won't be linear, but there will be some there will be some change in that velocity profile, like it may be like this or it may be like this, but here they have considered like what, a linear profile. It has been given in the question, so we will consider it to the profile to be linear. So what is happening, let us draw this. This is the first question. So what is happening, the inner cylinder is moving at a velocity of 300 rpm, and its radius is r and the thickness is t. This the different, not thickness, it is the distance between the two cylinders. It is already given, the gap is given as 0.15 centimeter, right? So the outer diameter of the inner cylinder, that means it is given as 12. So this r is equal to 6, r is equal to 6 centimeter, right? So the inner cylinder is rotated at 300 rpm is already given here, and the torque is given as 1.8 newton meter. So determine the viscosity of the fluid, and what is said that just 1 second. So what said that L is far greater than the gap between the cylinder. It said that consider a fluid layer of thickness L. The thickness of fluid layer is L with a small gap between two cylinders. Take the wetted surface area of the inner cylinder to be 2 pi RL by disregarding the shear stress acting on the two ends of the inner cylinder, where L is the length of the cylinder. That means this is the cylinder, right? There will be it will be like this. So it said that the effect of the ends is not considered here, and it's also said that L is far greater than it means like that between the gap of the cylinder. That's why the effects of the end is ignored. Here L is given as 40 centimeter and inner dia is given as 12 centimeter. The rotations is given as 300 rpm and torque is given as 1.8 newton meter. So we need to find the viscosity. I'll give you 5 minutes. Like, have you understood the question? Have you understood the question?
No,
Hello.
no, ma'am, no.
Like, what doubt? Like, any question? Like, have you like any doubt that you want to ask specifically?
Ma'am, actually, either fluid is flowing inside or what?
Yes, the fluid is flowing inside that. That is a long cylinder. The fluid is flowing inside the viscometer, right?
Means between outer cylinder and inner
Inner
cylinder,
cylinder,
right?
correct. In that the velocity profile is drawn, so fluid is flowing over there, and we need to find the viscosity of that fluid itself. The torque is
Okay.
given, like what is the torque is given, the rotations of the inner cylinder is also given, the diameter and length, everything is given. So we need to find the viscosity. So I'll give you 2 minutes to solve this question. uh, can you solve this now? Simple mechanics will be applied because torque is already given. Okay, let us wait for 2 minutes. Let's see whether any one of you can solve this. Otherwise, we'll proceed with the solution. Let us wait for 2 minutes. Okay.
Yes.
Try to solve. Find out the formula of torque. like how it is related to the force, right? And how torque is related to force, and the force will be relating to the shear stress that is provided by the fluid. So we can apply Newton's law over there, shear stress into area, and in that shear stress we can apply the Newton's law. That means mu du dy, del u del y. And since the velocity profile is linear, so del u del y we can simply take as v by l. And so you can use this formula, tau is equal to mu v by l a into r, right? So this is basically force into r. So force is basically shear stress into area. So we have just written it as, so here Newton's law wave applied. So now this is angular velocity. Sorry, this is linear velocity. So linear velocity we need to link with angular velocity. So linear velocity is equal to angular velocity into radius.
RMA.
Yeah. So angular velocity into radius. So this angular
IDS.
velocity we can write as 2 pi n. N is the number of rotations into r, 2 pi nr. So just replace it over there. So you will get some formula like here mu is also already there. So mu you can find out from there. You can solve it now. Try. I've told you everything. You just have to solve it. Just put this formula velocity in this equation. If I consider this as equation 1, put the formula velocity, linear velocity in that equation. Okay, I'll give you 2 minutes then. Solve this. Do you have any doubt? Okay, solve this now. Then I'll explain you in details. I'll just be back in 2 minutes. If you're facing any problem, you can tell me. Anyhow, I'll be solving this. Has anyone solved it?
D, ma'am.
D. Yes, correct. Okay, so let's solve it now for ourselves. Okay. First of all, we already know that torque is equal to simple mechanics, force into radius, right? Force is shear stress into area into R. Shear stress we can write from Newton's law is del U del Y into area into R. Now, this can be written because the profile is linear. This can be written as U by L. L is the thickness of that fluid, right? Yes, the fluid layer thickness. So this we can write as V by L, V by L. So V, I have already told you, we can write as angular momentum into radius. Angular momentum is 2 pi into number of rotations. So this we will put here 2 pi n r upon L, 2 pi r L. Area is 2 pi r into length, the circumferential area where the change is taking place, right? Because this is the whole cylinder, right? So this is the area where the change will be taking place. This is the area, the whole lateral area of the cylinder. So this is 2 pi rl into r. So okay, so this mu is equal to torque. So if we will write this mu will be torque into L upon 2 pi whole square n number of rotations r cube L. So this is 1.8 Newton meter into 0.15 into 10 to the power minus 2 meter. This will be 2 pi whole square into 300. This is rotations per minute. So we will convert it to second. 1 upon second into 6 into 6 into 10 to the power minus 2 whole cube meter cube into 40 into L is 40, the whole length, into 10 to the power minus 2 meter. So if we will solve it, we'll get 0.158 Newton second per meter square. That will be option D. Okay, let's proceed to question number 2. In the same question, okay, so next question is, consider two identical small glass balls that is dropped into two identical containers. One is filled with water, another is filled with mustard oil. Which ball will reach the bottom of the containers first and why? Anyone? You can see the question. Anyone? One is water, another is oil. Which one is will reach faster?
B.
Hmm? Yeah, but why?
Because oil will offer more resistance.
Yeah, its viscosity is more. Let us get a if like in mathematical sense also. Let us solve this. Okay, so this is question number 2. So let's suppose this is a container, right? So this is the kinematic viscosity of the fluid. So if this is the glass ball, right? So weight will be that it will be acting on the glass ball is mg. There will be Bowen force, that is fp, and there will be viscous force fv. So viscous force will also resist the falling, and the Bowen force will also resist the falling. So fv plus fb is equal to mg, the weight. The viscous force will be given as 6 pi mu rv. You will like, I won't derive this will you will like see in the later classes when sir will derive. So it will for lower viscosity sorry velocity, this is the equation that we'll be using for viscosity. And for Bowen force means what? The density of the fluid, the volume of the volume of the body, sorry, the volume of the body that is immersed onto that fluid into G. So if we will consider that the whole body is immersed inside, then the volume that is the volume of the body that is inside, that will be the volume of the body will be same as the volume of the fluid. So what we can do is we can write it as density of the body, cause volume of the body, so density will also be same. So we can write it as density of body, volume of body into G. So if we will write in the main equation, that is in this equation rather, so we can write it as 6 pi mu rv is equal to 4 by 3 pi, say this is spherical, right? So 4 by 3 pi r cube into density of ball minus density of fluid into G. Right, so just we have converted m is equal to, like, what is mass is equal to density to volume, so we have just converted density to volume, sorry, volume into density is equal to mass, so we have just converted this mg, this mg this mg of gravitational force to density into volume. Okay, just one second. Sorry, this will be fluid, this will be for fluid. Yeah, so if we will write this, we can write this as 2 by 9 velocity, we can write as 2 by 9 r square rho b rho f g upon mu. That is velocity. If we'll take others into, like, others as constant, velocity is inversely proportional to mu. That means if the viscosity is more, the velocity is more. And almost all of the oils have 800 times more viscosity as compared to water. So with the viscosity of oil being more than viscosity of water, its velocity will be less. So yes, option B is correct. Let us proceed to question number 3. Okay, so I think question number 3 is visible. So what does the question say? A thin 20 by 20 centimeter flat plate is pulled at 1 meter per second. It is the plate in the middle, horizontally through a 3.6 mm thick oil layer. Total is 3.6 mm sandwiched between two plates, one stationary and the other moving at a constant velocity of 0.3 meter per second. So what is happening? It is a quaid flow, though there is one flat plate in between, also 20 by 20 centimeter flat plate that is in between, and that is also pulled at a velocity 1 meter per second. The dynamic viscosity of the oil is 0.027 pascal second, and the location where the oil is. So what we need to find? We need to find the location where the oil velocity will be 0. So if we can see in the profile, we can see that at point A the velocity will be 0, and another is at point where the top wall will be coinciding with the oil, right? At that point also velocity will be 0. So we need to first find those, that is also like, because of the no slip boundary condition, that is evident. But at point A, what is the velocity? Like velocity is 0. We need to find the distance, like we need to find ya basically. Let me magnify this a bit. So basically we need to find ya, the distance at which the velocity will be 0. Have you understood? Or do I need to explain it again? Anyone? Do you have any doubts? Okay, no doubts then. I'll give you 2 minutes to solve this, then we'll proceed with the solution then. Any doubt? You can solve it, right? Simple similar triangles concept you can use here. Like you can take this lower portion, the smaller portion to be a triangle, and mm, there is this section, right? This section. This is the bigger one triangle, and this is one smaller triangle. So you can take this into consideration. You can take similar triangles concept here because the angles are same. So after that, you can just applying similar triangles concept. You can find out why. Okay, let me give you 2 minutes for this. Anyone? Have you solved it?
Is it A, ma'am?
Let me see. Yeah, it's it. Jainuddin, I think it's your name. Have you solved it? If you can't solve also, then
Mm,
also it's fine. It's very fine. You can just tell me like what is the problem that you're facing. Okay, I'll give you 2 minutes to solve this. I'm here only. You can ask any doubt that you're facing. Okay, let's solve this because we have many more questions to solve today. Let's see. So, first of all, question number 3. So, this is one plate, this is another plate, and this is one plate in between that we are pulling at a velocity of 1 meter per second. This is stationary, this plate is stationary, and this is moving, wall or plate, anything. So, this is moving at a velocity in the opposite direction. So, this is 0.3 meter per second. This is 1 meter per second. Okay, so this this height is given as 2.6 mm and this is given as 1 mm. So the velocity profile, like this is to all total 3.6 mm. So the velocity profile that we are getting here is here, it will be like this. Okay, so this point, the velocity at this point we need to find. So sorry, this will be from here. No mistake. Yeah, so let's suppose we will name it as A, B, C and D, E, F. Right. If we will draw the magnified version of this here, then it will be like it will be like this, it will be like this, B, C. So this is 90 degree, this is 90 degree, this is E, D. I have drawn this wrong. Let us draw like this. So this is straight line. This will be similar. And this will be one small thing. Right? This is B, C, A, E, D, F. This is YA. This whole distance is YA. Okay. So now this triangle and this triangle, these are similar triangles. Why? Because both of these are 90 degree and obviously this angle are equal and opposite, so this angle will be similar, so this angle will be similar, so these are similar triangles, right? So if these are similar triangles, by similar triangles formula we can write ACAE. That means ACAE is equal to BCBCD DE, and AC is equal to what? AC is equal to YE, and AE is equal to what? A is equal to this one whole distance is h2, h2 minus ya, h2 minus ya. Okay, now BC is equal to what? BC means this distance. See, uh BC if we write, BC is the velocity VW, like BC is just at wall, and wall is moving at velocity of 0.3 meter per second. So per second, if we are taking per second, this velocity will be 0.3 meter. So we are taking per second value only. So BC we can write as 0.3. So because of no slip condition, and DE also in the similar fashion we can write it as 1. So YA upon H2 minus YA is equal to 0.3 upon 1. So YA is equal to 2.6 minus YA into zero point 0.3. So YA will be written as 0.78 upon 1.3, that means 0.6 mm. So the location where the velocity is 0 is 0.6 mm from the bottom wall. So this is option A. Let us proceed to next question now. In the previous question, the force that needs to be applied on the plate to maintain the motion is which of the following? The force that is in the force that needs to be applied on the plate to maintain the motion. The force that we are applying here, the force we are applying on this plate, this F we need to find out, right? Okay, so I'll give you 2 minutes. Like it's simple, very simple. Like the just the force balance. So the force will be shear stress into area, and shear stress will be for two plates, right? One is top plate and one is bottom plate. So there will be difference in velocity in the, like, shear stress is equal to dv dy, and this is linear profile, so there will be del v upon del L. So that distance is given between the top plate and the middle plate. So the top plate and middle plate, it will be velocity of the, like, middle plate minus top plate, and top plate, and the for the top plate, sorry, bottom plate and the middle plate, there will be difference between both of the velocities and the distance between them. So you can, in simple way, you can just add on both of the forces from the top plate and the bottom plate. So I'll give you 2 minutes to solve this. I think you have understood. Are you facing any doubt in this question? Simple, just the force balance. Okay, I'll give you 2 minutes to solve this. Have you solved this? Anyone?
1.62 Newton.
1.62?
Newton.
It will be kilonewton. Just check your unit balance. Oh, no, no, no. It will be Newton only. Correct. I'm wrong. It's millimeter, right? I was considering it micro. Okay. Let's solve this then. So it's option C, right? Yeah. Let's solve this. So what will happen is force force is equal to shear stress that is acting on the either of the plates into, that is tau into area. So there will be shear stress, that is a force for the upper plate and the force for the lower plate, right? For the upper plate, it will be shear stress into area. It is mu d del u del y into a. So this is like, it is a linear profile, so we'll write it as mu a into v minus velocity. I told you the difference in velocity upon h1. So who is coming now? Okay, so it is the difference in velocity upon the distance between them. So let us move to the, like, yeah. See, if we see the diagram, if we will note that, so it will be what? It is the H1. This is the H1, right? And this is the H2. So this is H1, and so we will write it as V minus 0 upon H1. So 0 why? Because the upper wall is at rest. So this is 1 meter per second. And what is h1? h1 is in 1 into 10 to the power minus 3 in meter, because this is 1 mm. So this will be 0.00108 into 10 to the power minus 3 Newton. So, sorry, 10 to the power minus 3 Newton. So this will be 1.08 Newton, not kilo. This is Newton. Okay. So for the lower, the force will be mu A into velocity minus the lower velocity. But if you can see that the lower plate is moving in the opposite direction, let's see, the lower plate is moving in opposite direction with a velocity of 0.3 meter per second. So this will be in the opposite direction, so we will take it as minus 0.3, and the distance between them is what? 2.6 mm into 10 to the power minus 3. So this will come out to be 0.54 Newton. So total force is, that will be given given on the middle plate, that will be 1.08 kilonewton plus 0.54 kilonewton. So this is 1.62, sorry, not kilonewton, newton only, sorry. So this will be 1.62 Newton, that is C. Okay, next question now. Kinematic and dynamic viscosities have the dimensions of which of the following? I've already showed you this, right? I've already solved it for you. Tell me which one of the following.
A.
Mm-hmm.
Sorry, ma'am. B.
Correct. Okay, so let's do this. We already did it. So anyhow, so this will be nu will be kinematic viscosity, that is meter square per second. That means L square to the power minus 1. And dynamic viscosity is tau upon del u del y, that means force per unit area upon del u del y. So that means what? That means m L t to the power minus 2 into L to the power minus 2, area to the power minus 2. Ml to the power minus 2 is for force, and del u del y is at L, velocity means L t to the power minus 1, and upon del y is L to the power minus 1. So this will just cancel out. So this will cancel out this one for minus 1. So this will be m L to the power minus 1 t to the power minus 1. Simple. So this is option B. Let's move to the next question now. So there are two groups, group 1 and group 2. So this group 1 contains the types of fluid, and group 2 contains the shear stress strain rate of the shear relationship of different types of fluids. So tell me which one of the matches are correct. Anyone? Can you tell me which one is the Newtonian fluid? This is very easy, right?
One is the Newtonian.
Which one?
One.
I'm,
Two.
which one?
Two.
2, right? Yeah. And which one is the dilatant fluid? Dilatant means which one? Which one? Tell me.
3.
Yeah. Dilatant is 3 and pseudoplastic is 4. And so Newtonian is 2. That means P is 2. Pseudoplastic means Q. Q is which one? Q is 4. That means Q4. And now R is plastic fluid. Which one is the plastic fluid? Tell me that. S is 3. So 5 is the plastic fluid, right? So for plastic fluid, it will be number 5. So in this, let me tell you the and also like see, shear stress we write as, this is question number 6, right? Yeah, shear stress we, so answer for this question, answer is option C. So shear stress we write as K del U del Y whole to the power n, right? K is what? Flow consistency index, and this n is what? Flow behavior index, right? So this we can write as such. So if we plot the diagram, this is for the ideal Bingham plastic, this is for pseudoplastic, this is for Newtonian, this is dilatant, and this is ideal fluid, and this is ideal solid. This one is ideal solid. This is ideal solid. This is ideal fluid. This is dilatant. This is Newtonian. This is pseudoplastic, and this is ideal Bingham plastic. Like ideal Bingham plastic is like toothpaste or chocolate, and pseudoplastic fluids example are nail polish or ketchup, and Newtonian is obviously water, and this is a common example. And dilatant fluid is like cornstarch. If you mix cornstarch in water, no, that a combination of that is a dilatant fluid, right? So for pseudoplastic, let me pick some another color. For pseudoplastic, n is less than 1. For Newton fluid, n is equal to 1, and for dilatant fluid, n is greater than 1. Cause viscosity will keep on increasing as we'll be applying pressure. Sorry, stress. That is, stress will be continuously increasing as we'll be applying strain, right? And see, I am talking about this n, right? So this is here it is strain, shear strain. So this means du dy, and it is shear stress we write now. Okay. Now let us proceed to the next question. So blood is a Newtonian fluid, and the rate of strain varies non-linearly with shear stress for blood. Which of the following are correct? Anyone?
A is false, R is correct.
Is false or is correct? Correct. It's done. So let us proceed to the next question now. So you are to examine two statements carefully and select the answers to these statements. At the standard temperature, the kinematic viscosity of air is greater than that of water at the same temperature, and the dynamic viscosity of air at the standard temperature is lower than that of water at the same temperature. Can you find that out? Like I'll give you the values like density density of water is equal to 1000 kg per meter cube, and like viscosity of water is approximately 50 times, sorry, viscosity of water is approximately 50 times of that of air, right? So 50 times of that of air, and another is density of air. Density of air is 1.2 kg per meter cube. So I think you can find this out now. You can take the ratio and find it out. Anyone? Anyone who can answer?
Both correct, ma'am.
No. Acha, both are true. Yeah, yeah. So can you tell me how did you find the at standard temperature the kinetic viscosity of air is greater than that for water? How you have solved it?
Mu by rho, ma'am.
What?
Mu by rho.
Yeah, correct, correct, correct. So let us solve this. So nu air upon nu water we need, right? So this is mu air by rho air into rho water. If you will just denominator will take a top. So this is water upon mu water. So this is 1 upon 50 as it is already given into 1000 upon 1.2. So this will be 1000 upon 50 is equal to 20. Though the viscosity, we know that the dynamic viscosity of air is lower as compared to for water, but in case of kinematic viscosity, it is just the opposite. That is for air, it is greater than that of water, because we can see that nu here is equal to 20 times of nu water. So answer is option A. Excuse me. Yeah. Next question is, which among the following statement is true related to Reynolds number? Reynolds number is the ratio of which of the forces?
B.
Yeah, correct. Next question. Which among the following statement is correct for the flow over a flat plate? Flow is considered to be inviscid only outside or only inside or in the entire region above the flat plate?
Only inside.
Inside, inviscid? No. What do you mean by inviscid? Tell me. Inviscid means velocity won't sorry, viscosity won't change. So inside the boundary layer viscosity changes, right?
Yes, ma'am.
So inviscid will be outside the boundary layer. That means it will be option A. That is, inviscid means, remember, inviscid means not viscous. That means the viscosity doesn't change. So viscosity is there though, but viscosity does not change with the strain, right? That will be outside the boundary layer. So it will be option A. Let's go to next question. So these were very simple. So which of the following, which among the following is the correct expression for the apparent viscosity? See, this sir have already taught in class, right? So I already gave you the formula that which one?
A1.
A this is for the, this you are telling for shear stress, but we are not telling for shear stress. We want apparent viscosity. So shear stress is equal to K into du upon dy whole to the power n. So from this formula, how we can find out the apparent viscosity? Tell me that.
B, ma'am.
D. Let me check. Yeah, that's correct. So this sir I've already told you in the class, though I am just repeating. So this is K. We can write this as del u del y whole to the power n minus 1 into del u del y. Simply, nothing else. 1 minus 1 plus 1. That means n only. So this we can write as apparent viscosity. So apparent viscosity is equal to K del u del y whole to the power n minus 1. Right? So this is option D. Next question. So, which among the following statement is correct regarding thixotropic and rheopectic fluid? Which one is correct? Which one is thixotropic? Apparent viscosity decreases or increases? And the vice versa will be true for rheopectic.
Thixopectic increases. Sorry,
So,
decreases, ma'am.
rheopectic or thixotropic? Which one you are saying? Like, you tell me the option. Which one you think is true?
A, ma'am.
Yeah, correct. So, this also, sir, I have taught you in the class. Let's go to question number 13. So a body weighing a 500 Newton slides down at a uniform speed of 2 meter per second along a lubricated inclined plane, making a 30-degree angle with the horizontal. This is simple mechanics. The viscosity of the lubricant is 0.1 kg per meter second, and the contact area with the body is 0.2 meter square. Determine the lubricant thickness assuming linear velocity distribution. It's very simple. So it's similar to the question that sir taught you in the class. So this is the angle that a surface is making with the horizontal, and this is the body that is sliding down. This is the body, and this is the lubricant. This is lubricant. Lubricant is there in between the body and that surface. So this thickness of this layer we need to find out. So it is 2 meter per second, is falling down at 2 meter per second. It has weight in the bottom, that is 500 Newton, and so its thickness we need to find out. Let's suppose the thickness is, this thickness is h. So h we need to find out, and this area is also given as 0.25 meter square, and the mu of the lubricant, that is the viscosity of the lubricant, is given as 0.1 kg per meter second. So how to find out that h? Anyone? I've already drawn it for you, like how the diagram will be looking. Free body diagram rather.
0.2.
Point.
2.
Correct. It's very simple, very simple. So very good. You, Priyanka is very good in this. So this is 90-degree angle. So if this is 90 degree and this is 30 degree, then this is 60 degree, right? So if we will, we know that tau is equal to mu du dy. So tau is equal to force per unit area mu du dy. So force per unit area is equal to mu. So this is it is said that the linear velocity distribution is there, so we can write it as v upon h. So h is equal to what? H is equal to mu velocity into area upon force. So force that is present here is only weight. So force, sorry, not weight, shear stress. So we can it is the no, here only weight is acting. So for the body, so we are taking free body diagram of the body itself. So for the body only weight is acting. So we need to take the tangential component of that force. So 500 sine 500 actually cos 60 degree. Cos 60 degree means sine 30 degree, anything you want to write. So 0.1 into 2 into 0.25. So this will come to be 0.2 mm. So yeah, this is option D. Let's proceed to the next question and last question this is. So this is the last for today, and 5 minutes left. So we will take 2 minutes to answer this and then we'll proceed with the solution. For the following test data, determine the bulk modulus of elasticity. Like we need to determine what bulk modulus of elasticity. It is given that at 3.5 mega Newton per meter square, the volume is 1 meter cube, and at 12 mega Newton per meter square, the volume is 0.99 meter cube. So which of the following is true for the bulk modulus? We just need to find the bulk modulus and apply the formula for that. So it's very easy, right? Just directly we need to apply the formula of bulk modulus. Okay, I'll give you 2 minutes to answer this, then we'll proceed with the solution. This is question number 14. Anyone? Priyanka? This is the last question. Are you solving, Priyanka? Jainodin?
Yes, ma'am.
Tilakumar? Anyone solving? Yeah, Priyanka, solve and answer me. Jainodin, are you solving?
Yes, yes, I'm sorry.
Yeah, it's directly you have to apply the formula. So we know that formula
V1.
for bulk modulus, yeah, is equal to V1 del P upon del V, right? So just apply formula there. Where there will be V1, you will be applying P1. So it's like that. So you have to take difference in pressure over there. So there are two conditions being given. So just we need to take those two conditions and take the difference of between two. That is del P, we need to take the difference between both of the pressure, and del V, we need to take the difference between both of the volume. That's it.
Yes.
Which one? Oh, I'm unable to understand. Again, repeat. Which one of the option you are thinking is right? Jainuddin? Okay. Priyanka, have you solved?
B, ma'am.
Yeah, correct. So let's do this, the last question. So P1 is given as 3.5 into 10 to the power minus 6 Newton per meter square. P2 is given as 12 into 10 to the power 6, not minus 6, 6 Newton per meter square. For volume 1, it is 1 meter cube. For volume 2, it is 0.99 meter cube. So delta P is equal to P2 minus P1 is equal to 8.5 into 10 to the power 6 Newton per meter square, and delta V is equal to V2 minus V1 is equal to minus 0.01 meter cube. And the bulk modulus of elasticity is minus V1 delta P upon delta V. So this is equal to 1 into 8.5 into 10 to the power 6 upon 0.01. So that will come out to be 0.85 into 10 to the power 9 Newton per meter square. So that is option D. Okay. So anyone is having any doubt for today's class? Like anything that you want me to repeat or you have not understood? Okay. So let us end today's session, and I'll meet you all next week, same time at 7. That means Friday at 7 p.m. Use the same link to join. Okay, guys. Bye bye.
Thank you, ma'am.
Welcome. Bye bye. Welcome.